Greetings to everybody watching me right now. Welcome to Shexa's YouTube channel. Please like, comment, share and subscribe to this YouTube channel. Today we are going to look at microprocessor x86 microprocessor programming, where we will be focusing on accessing memory. And the previous lecture we talked about accessing memory, but we didn't complete this phase of arrays, or this topic of arrays. When we are declaring variables and arrays, we will be naming memory locations. So we need to talk about arrays. So the areas that will be covered include array definition or array declaration. By the end of this lecture, you shall be able to define theoretically to say an array is defined as, and practically to declare an array through an APL program. Right, then we look at some array code examples, practical programming of arrays. Then we look at the dupe directive, which is used to dupe operator, which is used to declare large array variables. And then we look at a variable address access, and finally we look at a constants as a bonus concept in this lecture. So like, comment, share and subscribe. Before we start to look at array definition or declaration, please add more likes. If you didn't like, just give me a like if you like it. If you don't, just leave it like that, or you can give me a comment, a positive comment. Maybe you've gone through the first lecture, or any of the lectures that I provide online, or those that I provide physically in class. You may give a comment or suggestion to say, my God, improve on 1, 2, 3 things. Share with your family members, colleagues, and all those that you think need to have access to this content. Subscribe if you haven't subscribed already. Thanks to those that have subscribed already. I hope 2021 is having great opportunities for you and everyone else, in Jesus' name. Say amen. Right, so I will start by giving you a takeaway, or I'll give you a homework or a task, and I assume that you are watching me while at home or wherever you are watching me from. Just take this and work on it. Write in ALP. ALP stands for Assembly Language Program, to find the average of any 4 numbers in an array. So we are having an array which has got 4 values, and these values are supposed to be added. So you're just calculating the sum, and then you divide the sum by the number of items in an array. So that's it. That's a takeaway, TA for you. Right, now what is it that we call an array? An array is defined as a series of variables. An array is a series of variables. So this series of variables has got many variables, but all the variables are using the same variable name. What only differs is the index or the indices. Right? So an array is just a series of variables that uses the same variable name. Right? So let's say you declare a variable that that will take care of strings. That variable is an array because each item in a string is treated independently. So we treat all those. So having a series of those characters means we're having an array. So we can say a text string is an example of a byte array. Each character is presented as an ASCII code value, and the code values ranges from 0 to 255. What we mean by this is a small letter a is represented by a certain ASCII code which is within the range 0 to 255. Any character, comma, hash, ampersand, star, n, q, and the other thing is small letter a and capital letter A. They are represented by different ASCII code values. They are represented by different ASCII code values. Let's now look at the syntax that is used to declare an array. So here's the syntax. You first give a name to what? To your array. So you say array name, then put a space, then you say array value sizes. Since we said it's a series of variables, so each variable is of a certain size that we are going to define here. So what is common to these variables, what is common to the series of variables is the array name and the sizes of these variables. And what is not common is the indices. The index for the first value is 0 and it's different from the second value, which is 1, and it's different from the third value, which is 2, and so forth up to value n. So what we do is we say array name, define byte. That's how we do it, like what we did in the previous lecture where we talked about how one can define a variable. I'm sure we've done that, or we've covered that in the previous lecture. Then define byte, define word, to dt and so forth, the dd and so forth. Then you put a value. You don't tell your compiler to say, your assembler to say, I want strings, I want characters. You may mix them up to say value 1 is an integer, value 2 is a character, value 3 is a string, and so forth and so forth. So this is how we declare an array. This is how we declare an array. We don't assign the size or whatever you may think of as it is done in C, C++, and maybe Java and other languages. So with this, let's now look at array definition examples. So you now know the syntax. May you please share with me the syntax on the chat section. Share with me the syntax on the chat section or in the comment section, so that I observe that you are understanding what I am teaching you here. Okay, that's fine. So here is an example. Example number 1. What do we do? We start with a variable name. Let's call it Shexa. So Shexa is our variable name, right? And these are the values that we are having in our Shexa byte variable. So Shexa is of size what? It's of size byte. If you look at it there, Shexa is a variable of size byte. And then what values do we have in our array? We have 48, 65, 6CH, 6CH as well, and then we have 6FH00H. So H stands for hexadecimal. It's just telling our assembler to say this value is in hexadecimal number system. Right. So this is just an example of how one can define an array. And here is what happens if you write such an instruction in an emulator or whatever you are using to program the microprocessor. So the first thing that we talk about is the variable name itself, the array's variable name, or as we defined variables in the previous lecture, we said a variable is just the name of a certain memory location. So Shexa as a variable is declared on that line of code is a name for a certain memory location, right? So since we said an array is a series of variables, now we are saying Shexa is the first memory location, or is the first variable, and then Shexa square brackets 0 inside, that's also the first. So Shexa and Shexa index 0, they reside on the same memory location, right? And then we have Shexa index 1. So Shexa index 0 has got this value 48, as you can see. Shexa index 0 has got 48. Shexa index 1. So these are the variables that we have. Shexa index 0, it's residing at a certain byte in memory, and there exists a memory location value which correspond to Shexa index 0. Shexa index 1 has got this value is initialized in this line of code, and Shexa 1 is a variable which has got a different memory location from Shexa 0 and other Shexa variables that we have declared here. Same applies to Shexa 2, Shexa index 2, Shexa index 3, Shexa index 4, Shexa index 5. So these are the values that we have inside our memory locations or inside our array. So these are the actual values in hexadecimal number system, right? Since our x86 microprocessor deals with numbers in hexadecimal values, everything that we are going to type in or anything that we program is dealt with in hexadecimal values. So whether you declare a character, you declare a string, you declare whatever the type of value, decimal value, whatever, it's converted to hexadecimal, and the moment you initialize it, it's converted to hexadecimal value. So these are the values, but here we have already declared Shexa and initialized it to these bytes. So each value is 1 byte. So we have 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. Like I said, to say all these variables, this one, this one, this one, this one, this one, and that one, they share the same name, which is Shexa, and they share the same size, which is byte, 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 byte. Right, so we are done. So Shexa, we are done declaring this variable. Then let's look at another example. Let's say we have king. So king is an exact copy of the Shexa array. So when the compiler sees a string inside quotes, it automatically converts it to a set of bytes. So by converting this to a set of bytes, we are now saying that's an array. You see, so you will see why I'm saying king DB is an exact copy of Shexa array. So I am sure that you understand that king is the array name, and then we are defining the size of our byte variable. Then we assign it to this string. So this string has got H, E, L, L, O, and a 0. Right. So a 0 is a what? Is a decimal value, and a 0 in hexadecimal is still a 0. Then these values, they need to be converted to hexadecimal values. So H is converted to a certain value in hexadecimal, and that value is the one that exists within 0 to 255. That is the ASCII code, as said earlier. So the ASCII code for capital letter H is 48. So you will see. Let's now look at our king byte variable, king array variable. So king index 0 is H, and H in hexadecimal is 48, and then E, small letter E in hexadecimal is 65, and then 2, king index 2 is 60, which is L, and then we have L as well, which is 60, and then O is 6F in hexadecimal. Then our 0 is still 0, 0. Right. So you can observe that these two arrays, Shexa DB and king DB, they only differ on array names, but the values are just the same. It's only that king is initialized to a certain string, and Shexa is initialized to hexadecimal byte values. Right. So this is how the compiler or the processor treats array values. All right, so let's get into an example. Right, let's now write some code. Let's now access values in an array. To say, let's access Shexa index 4 or Shexa or king index 4. So let's write the instruction. So we have the instruction which is move AL Shexa index 3. What do you think is the value, that is, what do you think we are doing with this instruction, which is saying move AL comma Shexa index 3? What are we doing? I want to see answers, right? 1, 2, 3, 4, 5. I'm done counting. So what is happening is we are moving the value that is stored in variable Shexa index 3, which is this one. This value, this one 60, is being moved to AL. So this is what happens. This is what happens. So when you run this instruction, AL is going to take 60. Right, so let's now try to access king array. So we say move, in this case you can since we talked about variables that are used to access memory, you can also use any of the memory index registers, that is bx, si, di, pp, to access the values of an array, or to access the values that are within the memory and labeled with an array, with the array name. So here let's use si like that. This is the instruction that we are talking about. Move si, 3, and then this is what happens with this instruction. We are moving 3 decimal value into si register, which is source index, right? So the next thing is we are now moving the value that is at king index value in si, which is 3. So we are taking the value that is at king index 3, and the value that is at king index 3 is 6c. So 6c is the one that is going to be moved to AL. Right, so why are we saying king si is king index 3? Because si's value is 3, right? So we are taking the value that is at a memory location named king si, king index 3, sorry, then it's moved to AL. So this is what happens. So you can see that this instruction and that instruction, they give the same result. It's just that on this one we are using si, or we are using memory index registers to register to access our memory. So let's see what happens from scratch. Si, you move 3 to si, then we say we move value at that index to AL. Right, so I hope you are understanding what is happening here. I hope you are enjoying this lecture, this practical lecture. So theoretically you now understand it, programmatically you now understand it, but let's now get into the emulator and write some code. Let's get into the emulator and write some code. So before we get into there, this is what we are going to see in the emulator. We have our data segment, which is this one. Then we define our variable called king, and king is of size byte, and we've initialized it to hello and 0. And then we declare another variable that we call Shexa, as indicated earlier. And then Shexa is initialized to these values: 48H, 65, 6CH, 6CH as well, 6FH, 00H, with H representing the number system, which is hexadecimal number system. Right, we get to the code segment. So in the code segment, that's where we are writing our instructions. And you observe that when we emulate this code, the emulator will start from the first instruction inside the code segment. Right, so what are we doing here? We have declared our variables in data segment. Data is stored in memory, and which memory? The memory locations labeled by these variable names. And what are these variable names? King and Shexa. So Shexa is the king Shexa. Walla, thank you very much for the likes, for the comments. I love you, I love them. Keep them coming. Right, so boom. What are we doing now? We are now saying move to AH the value that is in king index 0. So we are moving H, and H hexadecimal value is 48. So 48 is going to be moved into AH, and then we go to we try to access the values in Shexa array. We try to access the values in Shexa array at the value that is at Shexa index 0. We are moving it into AL, and the value is 48H. So we expect to see 48H in AX, or in AH we expect to see 48. In AL we expect to see 48 as well. Same applies to other instructions. King index 1, Shexa index 1, so E is 65, Shexa 1 index 1 is 65, so BH and BL must have 65. Then CH is receiving the value that is at king index 2, which is 6C. Same applies to, in 6C is L, and L in hexadecimal is 6C. King index 2, that's L in hexadecimal is 6C. So CH will have 6C, CL will have 6C as well. And it's so unfortunate that this instruction is not visible because of this lingering comment button or image, right? So, but same applies king index 4 and Shexa index 4. That's what is being moved into DX register. So let's get into the emulator. Let's open our emulator and see exactly what is there. Right, so that's what we have. I think and hope that you are seeing this. So let me just increase the font, but I think this one is okay. This font is okay. I don't know if you aren't seeing what I'm if you are not seeing what is appearing on this. If you aren't seeing my code, please tell me in the comment section, so that next time I will increase the font to a bigger size. Right, so these are the instructions. I think we have talked about all these instructions. Let's now emulate and observe what happens in our emulator, which is representing what happens in the processor. Right, so this is it. We say single instruction, what happened here. Right, so we reload, and then we, right, so the first thing we execute the first line, which is king 0, and in HH we have 0 0. We expect to see what? H getting into AX, but H in hexadecimal value, capital letter H in hexadecimal value is 48. So we say single step, we see 48. AL Shexa index 0, we have 48 as well. So that's it, as you can see it here. Without increasing that size, we also increase the font, but it's not happening that way. So 48 in AX, right? Then let's go to king index 1, that is E, and E in hexadecimal value is 65 according to ASCII code values. So if you run it, you will see 65, and then Shexa index 1 is got what? 65. So we execute it, we see 65 and 65. Then same applies to king index 2, L is 6C, so we see 6C getting there, 6C also gets into that, and then we are left with O. Is it O or what? 0, 1, 2, 3. So 3 is skipped here. 3 was skipped there. So let's just run king index 4, which is 0, 1, 2, 3, 4, which is an O. And O is 6F, and 6F is moved to DH. Same applies to Shexa index 4. So you see, that's exactly what we have discussed earlier, and you can observe that these two array variables are copycats. So you can observe that these two variables are identical. Right. So we are done. We are done on this one. Let's now get to another example, or maybe using the dupe to declare large arrays. So syntax for using dupe. Dupe is more like duplicate. So what are we doing? We're duplicating values. This one is very easy, simple. I hope you will enjoy it, and you have already enjoyed what we have covered so far. Right. Let's proceed with the syntax for dupe, and this is the syntax. We start with a variable name, and then we say dbd whatever, that is variable defined size. Then we go to times, the number of times you want to duplicate a value, right? And the value, we say dupe, and then inside the brackets, the curved brackets, we put the value that we want to duplicate, or the values that we want to duplicate. So that's syntax for declaring large arrays using dupe. We say variable name, Shexa maybe, or my numbers, or my prices, or whatever you want to put there. Then you say db dw, that's variable defined size, or defined size. Then you tell the compiler to say, I want this number or this value to be duplicated this number of times. So if you want it to be duplicated only once, then why do you want to use dupe? But if you want to have it repeated twice or more, then you use dupe. So times is at least 2. If you put 1, then that's fine. Dupe, you put dupe is not more like our operator, or the keyword that is used to repeat the values that are within the curve, that are to be put in the curved brackets. Right. So let's look at an example where we have nums db6 dupe 9. Think about it. What is it that is happening here? We've talked about the syntax, and here we have the example. What is it that is happening? We are declaring a variable called nums, right? And this is more like an array variable called nums of size byte, and it is having 9 duplicated 6 times, right? So nums array variable is of size byte and is containing, or is initialized to 6 nines. So let's see how it goes. So this is what happens. Num 0 is 9, num 1 is 9, num 2 is 9, num 3 is 9, num 4 is 9, num 5 is 9. Wow! So we've duplicated 9 6 times. So this is what happens within your memory. So if you want to access the value that is at nums 2, then what? then what happens? If you want to access that value, you then take 9. If you want to access nums 4, you get 9. If you want to access nums 0, get 9. So traditionally we say, maybe if you want these values, you may say nums db, then you start to say 9,9,9,9, 6 times, which takes you more time if you want to declare very large arrays with repeated values. Maybe you want to say you want to repeat 70 times, right? Will you write an instruction with commas 9,9,9 70 times? You can't do that. So you just write a small portable instruction like this one. So if you want to declare a large array, you can use dup operator. The syntax for dup I gave you. It says variable name, then you say, you define or you give us the size. You define the size of your variable. Then you state the number of times you want the value to be duplicated, and then you say dup. You tell us the value to be duplicated. Then it happens that way. Right, let's look at the actual code now. So this is the actual code that we have here. This is num. This is the same instruction that we have discussed. In data segment, we declare our variable and we duplicate 9 6 times. Then we move the value at index 4 into AL. Let's run it and see what happens. So I will open the code here. Sorry. Right, so we emulate it and check what happens when you run it. Right, so we've declared our variable called nums, and it's of size byte, and it's duplicating 9 6 times. All right, so in AL we expected to see the value that is at index 4. And what is the value at index 4? It's 9. 9 is inserted into AX. That's it. We are done on that example. All right, if you want to check the value that is at index 4 is here. 9. Right, let's now look at another example, nums. Let's now look at this example. This example is now duplicating several numbers. So I'm repeating what I've declared. Excuse me. I've declared a variable called nums. It's of size byte. It's repeating some numbers 2 times, and the numbers to be repeated are 9, 4, and 7. Now I want you to think about it. Take a paper, write the answers, or you may put the answers on the chat section, or you may put them in the comment section to say how are these values repeated. Are we going to say 9 9? That is 9 at being at index 0, another 9 being at index 1, then 4 at index 2, another 4 at index 3, 7 at 2 last indices. Or we're having 9 at index 0, 4 at index 1, 7 at index 2, then 9 again at index 0, 1, 2, 3, 4 at index 4, 7 at index 6, 5 rather. So let's check. This is what happens now. We have them that way. At index 0 we have 9, at index 1 we have 4, at index 2 we have 7. So we have our values, our first set of values. Then we start again, we repeat for the second time. So that's it. So if we want to access the value at index 4, which value do we get? Answers quickly. The answer is 4. You see it. So let's get into, or something wrong happened here. Let me just click and check. I think this code is not the one that we are supposed to see. Right, so it's okay. I will just edit it. It's 947. Was it 947? Click here and go back. 947, right? It's being repeated twice. So let me have it here. It's being repeated twice, and the values to be repeated twice are 947, like that. And then let's emulate it and check the value that is going to be moved to AL. Let's check the value that is to be moved into AL. So we have 9 at index 0, 9 at 4 at index 1, 7 at index 2, 9 at index 3, 4 at index 4. So at index 4 we expect to see 4 being moved to AL. Oh, perfect. That's it. We are done on this example. Let's save it. Right, so that's it on that example. Let's look if we have another example. Right, let's now repeat 9 and 4 3 times. I think you now know how it's going to be repeated. It's going to be repeated that way: 9 4 9 4 9 4. So 9, we have 9 3 times, 1 2 3. We have 4 3 times, 4 4 4. So 4. So if you want to access the value at nums index 4, what do we get? Right, so these are the instructions, the ones that are underlined there. This time the code that is appearing here is the correct one. So let's run it. Now we are trying to access the value that is let me write something that I thought about. 43. Right, so we are trying to access the value that is at nums index 5. So let's open the code here and emulate it. So when we emulate, we get this window, and this is the other window that we're going to get. Right, so what we have here is this. We have 9 at index 0, 4 index 1, 9 index 2, 4 index 3, 9 index 4, 4 index 5. So at index 5 we expect to see 4 being moved to AL. So let's run it. Perfect. So maybe you may want to change here to say, let's check index 4. What happens? Run it. Check AL here. 9. You see, so that's it. That's how the data is arranged. If you want to see the variables that you have, you may click here. You emulate, you may click here, and you will see that we have our nums as our as our variable, and 9 is the first value in our array. So the first value is the one that is shown here. Other values, they are not shown, they do not appear. So that's it. We then let's not save changes. So that's it for what? For dupe and declaring large arrays. Let's now look at these other examples and how we could actually have written it. So this is the simplest way, or this is the modern way of writing, of declaring large arrays with repeated values or duplicated values. So here we are having an alternative way of declaring such a variable is that way. So look at it. The number of instructions in this way, the number of characters in an instruction varies a lot. We may have if you want to have 20 items in our array, we will type all the values one by one. But with this way, you just change here and change the values that are to be duplicated. Another way is this one. Another example rather. You see, if you want 1, 2 to be repeated 5 times, the simplest way or the modern way, and here is the ancient way. Let me call it that way, an ancient way. So it's easy to use dupe. So dupe simplifies your coding. Right, so let's now look at what? Variable address access. So we have declared our variables and we want to know where exactly is my address. Where is the variable nums stored? Where is the variable num index 0 stored? Right? So since we said what? We said an array is a series of variables. So variable index 1 is different from the value at variable index 1 might be different from the value at variable index 3. So these are the instructions that we use to access the address of a what? Of a variable. So LEA is just saying load effective address. So we will be loading an effective address to a certain memory location or to a certain register. And offset is another instruction that is used for the same purpose, but they use different syntaxes. They use the different syntax. These operators are used to access variable addresses. Both these can be used to get the offset address of the variable. Load effective address is more powerful because it also allows you to get the address of an indexed variables. Getting the address of the variable can be very useful in some situations. For example, when you need to pass parameters to a procedure. Right, let's look at load effective address syntax. We just say load effective address into bx from. Load the effective address, we are saying load the memory address of variable 1 of var1 into bx. So we get the address of var1 into bx. So like I said earlier in the previous lecture, you may say, I know where Mr. Shexa stays or where Shexa stays, right? So Mr. Shexa or Shexa being the name, that's the address, right? So that's the name, sorry, but there is a number that is used by console to identify my address or my location. So there is a name and a location number that corresponds to the name given. So variable name var1 is just a label to a certain location. Now we want to retrieve the location itself and put the value that represents that location into bx. So that's it. And then let's now look at a code example. That's the syntax. Is that a syntax? No, I made a mistake of saying syntax and giving an example instead of a syntax. Then destination G, destination, then variable. Right, so this is the syntax. We say load effective address from load effective address of this variable into destination. Load effective address of this variable to this destination. So the source of the effective address is this one. So here I can say, instead of saying variable, I can say a source of effective address. So this is the syntax. We say load effective address, then the source of effective address, and then the destination. So here is an example. Shexa, define word. We are just declaring our variable, and then the code that is used to now load the effective address of this variable into CX. So that's it. And you need to note that these registers can be used inside square brackets, the BX, SI, DI, and BP. They point to memory. So these 4 registers, like we said earlier, to say these are the only 4 registers that are used to access memory. And whenever you want to access memory, you use the square brackets, and anything that is within the square brackets represents the effective address or the memory location to be accessed. Now let's look at this example. We write what? We write our code. So this is a code example. We have declared nums db duplicating 9 6 times, and we're trying to have the effective address of variable called nums into AX, and then we load the value, the address of variable nums index 0 into BX. So like I said earlier, nums is the common variable name for our array, right? So nums is now what? Nums resides at a certain address, but this certain address is the starting address to say all the values in this array starts from this memory location. You get what I'm saying? So nums is residing at a certain or specific memory location or memory address, and nums is the starting address as well. So the value that is going to be inputted into AX and into BX should be or must be the same, because nums and nums 0 resides at the same arrays, or are just pointing to the same memory location. So let's get into the practical example. Right, so that's the code, the one that I zoomed on that. So that's the instruction, that's the code. In data segment, what do? We declare what variables, and then in code we write our instructions. So let's emulate it and see what happens. Let's emulate step by step. Right, so nums in AX, we want to see the address of nums variable. So if you want to check our variables, just click there. You will find that we only see nums as our variable, and the first value in nums is the one that is going to be shown in this. So you click on vars if you want to see the variables, and the variables will appear that way. Right, so let's go single step. So in AX0102, that's the address of nums, right? If we go single step, you will find that nums0 and nums, they reside in the same address, or they point to the same memory location. Then nums1, we just increase by 1 because we are moving to the next byte. So it's now 0103. Now nums3 is what? What is the address? Think now. Think, because it's just the next byte in memory. So we add a 1 to that, we have 0104. Then let's put into AX the address of nums3 variable is 5, and then into BX it's now 6. So that's how we access the addresses of our variables. Right, so I'm done with load effective address. Let's now look at offset. Let me correct the syntax here and say destination, then here say source of effective address. Right. Something like this. So the syntax is that one. We move to destination, the offset of this variable. So instead of saying source there, I can say the variable. Maybe it's just the same on the previous syntax. That is the syntax of the syntax for load effective arrays. Right, so the syntax is this one. You move to destination, and then you put the operator or instruction offset, and then you tell us the variable that you want to get its address. Then let's look at a code example. We define our Shexa word, and then we get the offset of Shexa and get it into CX. Let's now, this one is just repeated. Now we have offset. We are doing the same, but now using the offset instruction. So let's get the code, so that you prove that what we're doing here is correct. We emulate. If you emulate there, what happens is this. Right, so we go that way, then we get nums, which was what? It was 0102, right? Then nums 0 index 0 is still that 0102, 0103. So what we are checking here are these values. Don't get confused. I do not want to rush, so that you understand exactly what we are doing. Let me reload. Right, nums, we get it there. Nums 0. Don't get confused to say why is nums, why is it that nums address is identical to nums index 0's address. I think I've repeated this several times, and I'm going to repeat it for the last time. Nums is just the variable which is being shared by every variable, every array variable. Since we said an array is a series of variables, so these variables, they share the same name, which is nums. And by saying nums, we get to a starting address where the series of variables begins at, and then the index 0 is the first one. So that's why we have nums and nums0 having the same arrays. Now we put into cx the offset of nums1, which is 30103. We put into dx into dx the address of nums2. Nums3, we get it into ax, which is what, 0105, and then into bx we put that as well. So we are done on this concept, right? Let's now get into the bonus concept, which is what? Constants. Constants are just like variables, but they exist only until your program is compiled or assembled. After definition of a constant, its value cannot be changed. Since we said it's a constant, so the value is constant. Then the syntax used to declare a constant, you say constant variable name, and then you say equal is the derivative, then you put the expression. Then here's the example. We can say Shexa is our constant variable, and then equi is our derivative, and then the value is 1, 2, 3, 4. Whenever you say Shexa, you are now referring to 1, 2, 3, 4. You cannot change the value of Shexa variable. Let's look at this code example. Here we have k, which is equal to 0, 0, and then we have move si. We move k's value into si. That is, we are moving 0, 0 into si, and we move 0, 0 again into al. So that's it. If we click there, right, so this is it, right? These are bonus concepts, right? Bonus concepts. So let me just say bonus concepts, because we are going to talk about some concepts that I think are important for you, since I gave you a takeaway earlier, right? So if we execute that and run it, if we get the code, right, so what happens is this: we have declared our array ar, defined byte, and we have values 1, 2, 3, 4. So this code is used to add the values that are within an array. So we're adding 1 plus 2 plus 3 plus 4, and what do we get? 7, 10. Get a 10, right? Right. So here is the ancient way of adding the contents of an array. So it's just a hint. I will leave you there and you complete the takeaway, right? So you say, I will say ancient way of adding array contents, right? So we declare our what? we declare our what's that? We declare our variable, our constant. Here we declared our array, here we declare our constant k, and then next we move 0 into 0 value into AL. Instead of that, we can put our k here. Then AL, we now add the value at index 0 into AL, which is we are adding 0 plus 1. Then we say the 1 that was added plus 2, we get a 3. And then we say a 3 plus a 3, we get a what? A 4. And then a 4 plus 6, we get a what? We get a what? A 10. So let's try and see if you execute it to say, do you get that same value? Right here. Right, let's go step by step. We move into AL. What are we putting into AL? 0. Then let's check 0 is there now, which is the value of k. And then what happens? We add what? 1 into AL. 1. We add what? Value at index 1, which is 2. 2 plus 1, we get a 3, I'm sure. Alright, so at index 2 we have 3. 3 plus 3, we get a 6 here. Right, 6 plus 4, we get a 10, and the 10 in hexadecimal is it must be A. Right, so we have our sum. So we have added what? The contents of an array. Now if you want to complete the takeaway, you'll find your own way out, but this is the ancient way. So let's just comment it. Let's comment it, and do the modern way and apply the modern way. Right, so the modern way is this one. Let's emulate and start to run it. Right, so what is happening is this is array declaration and initialization. We cannot talk about that, you now understand it. Right, so we are saying move what? Move 0 into SI. Okay, SI is this one. We are moving what? 0. It's already there, so it doesn't change. So move 0 into AL. We are clearing this AL. Right, we are done. Now we add AL, we add the value at array index 0 into AL. So we say single step, we add at index 0, we have what? We have what? We have 1. At index 0 we have 1. So we've added 1 into AL. We increment SI by 1. So SI was 0 and it's now 1. And then we go back. SI, look at SI here. It will increment by 1 like that. And then we look back to this label, which is called here. Then we go back into AL. We now want to add SI is now what? SI is now 1. So meaning to say we are now saying array index 1 because SI is 1. So we are now moving at index 1, we have what? 2. Sorry. Sorry for that. So at index 1 we have 2, and 2 is now being added to the value that is within AL, and then we say single step, then we have 3, and then we increment SI. SI was 1, and if it's incremented by 1, it's now what? It becomes 2. Now we get back to that. It's now array at index SI is 2, so it's array index 2. With index 2 we have 3. We are now adding 3 plus the value that is in L, which is 3, we get 6. So we run, we get a 6, and then we increment our SI, and then we look back. Our SI is now what? SI is now 3. We are now adding the value at index 3, 0, 1, 2, 3, which is 4. 4 plus 6, we get a 10, and the 10 in hexadecimal is A, like that. So that's it. That's the modern way of adding. So if we keep on running, in other things we still have values in that array. Right, thank you very much for having time with me. I don't want to save any changes. Thank you very much for having me. So I say thanks to you. Don't forget to like if you like it. Your heart is the one that knows what you're feeling. Like it, give comments, suggestions, and so forth. Share with your colleagues, friends, and whoever you think needs to see this content. Please subscribe to this channel so you do not miss any video that I upload on this channel. Please enjoy the rest of your day. Enjoy your time. Goodbye. May God bless you. I love you all.